Okay, all right. What I wanted to talk about today is just getting started on derivatives of functions of multiple variables. The other day we looked at functions of many variables, kind of took an introduction to that. Here's a graph, here's a picture you saw the other day. So most of the time in this course we'll focus on functions of two variables, as it kind of provides a nice blueprint for what happens in general. And plus, we have a kind of geometrical picture as well. So, a function of two variables is a function that assigns to every ordered pair of real numbers, x, y, a unique real number, f of x, y. The associated surface is a collection of points, x, y, z, where the z coordinate is given by the value of the function. And function of two variables, you can think of it as a machine that takes two inputs, x and y, which are independent from each other. It does something and produces an output called z, which is the value of the function. The other day, I showed you different ways to look at functions, different ways that they're portrayed. So we often look at the surfaces associated with functions. There are also these kind of contour plots, the weather diagrams. I showed you the way a contour plot is made. Think about taking the surface and slicing through with planes parallel to the XY plane, and uh, and then wherever the plane slices through the surface, that determines a curve. We project all those curves down to the XY plane and plot them, and we get a contour plot. Okay, now, to understand derivatives of multivariable functions, let's start by taking a look at derivatives in one variable. I'll just remind you of like the ideas that you saw in Calc 1. So in Calc 1, you start out looking at functions. In Calculus 1, a function is just usually a function of a single variable x. The output variable is y. And calculus is kind of the study of how functions change their behavior as you change the input. So, taking this value x, think about adjusting the value of x slightly. So we pick a different value of x which is nearby, kind of fiddle around with the input, and that's going to have some effect on the output as well. So if I plug in x prime instead of x, the output is going to be some number y prime. This is the value of the function at x prime. And if it's a reasonable function, you'd expect that if x prime is close to x, that the output y prime will be close to y. Okay, changing the input produces a corresponding change in the output. And the derivative is telling us something about like the relative change, how quickly or slowly the output changes relative to the input. So we often like we'll look at the change in x, delta x. That's going to be x prime minus x. And we'll compare that to the change in y, y prime minus y. And then we say, well, okay, we look at the ratio of these. This ratio tells us something about how quickly or slowly y changes relative to small changes in x. And then, looking at this, if we look at this for values really close to x, sort of in the limit as x prime gets closer and closer to our original value x, the limit is the derivative, dy dx, in Leibniz notation, and it's in Newton's notation, f prime of x. Okay, so the derivative is telling you, it's just giving you information about how the output changes relative to changes in the input. If the derivative is zero, it means that the output doesn't change. If you fiddle around with the input, in other words, the function is constant at that point. And if the derivative is positive, it means that increasing the value of x will give you a corresponding increase in the value of y. If the derivative is negative, it means increasing x results in a decrease in y. And then ultimately, the size of the derivative tells you how fast or slow these changes occur. So so that's basically what a derivative is telling you. Like you guys know from Calc 1 that the derivative gives you it's a powerful tool. It's reasonably easy to compute for a lot of functions that we're familiar with, and it provides a lot of information. Okay, in the case of you know, functions of two variables, there's a slight nuance, and this is like what you see for other multivariable functions, namely that, suppose we want to think about how does the function change as we go to neighboring points. So say this is the point we're kind of interested at x, y, and we want to change that point. We'll look at a nearby point, x prime, y prime, and we want to plug that into the function and get, a corresponding output z prime. Okay, well, one difference between this case and the previous case is that, this new point, there are lots of different ways that we can head away from this point x, y. If this is a point in the XY plane, there's like a whole, so let's say that this blue rectangle represents a sort of a part of the XY plane, and here's our original point. That's our point XY, and let's say X prime, Y prime is this nearby point. This point can be in all kinds of different directions. There are lots of different ways we can head away from that first point to get to this new point. It turns out if you just travel in different directions away from the original point, the function can be, it can be increasing in some directions, decreasing in other directions, and it can stay constant in certain directions. So there's more to it than just like saying, well, what happens as x prime, y prime gets close to xy? We have to be a little more precise because there's sort of a more variables. In the one-dimensional case, by contrast, if this is a piece of the real line and we have our original point here, and then our new point is either going to be to the left or the right. So there's only sort of two different directions you can head away from the original point. In two or more dimensions, there's like a whole infinite family of directions. So eventually, we'll look at something called the directional derivative, which tells us how the function changes in any particular direction. But to get a handle on that, we'll start with the partial derivatives. So the idea behind the partial derivative is that instead of changing both the x coordinate and the y coordinate simultaneously, we're just going to change one or the other. So if we're trying to calculate the change relative to x, then we think about changing the x coordinate, maybe replacing A by some nearby point, but we're going to hold B fixed. So we're just going to go sort of in one direction, just fiddling the value of A while holding B constant. And if you do that, then the relative change that you measure in that direction is called the that's the partial derivative with respect to x at the point AB. Okay, um, so I guess what we're doing here is comparing like the old value f of AB to this new point f of A prime B. So notice that B stayed fixed. All we did was change A to A prime, and then the relative change in the function is measured by this partial derivative f sub x. Now this x here, in this notation for the partial derivative, AB represents the point that we're thinking about. We're trying to figure out how does the function change near this point AB. Here's our function f. Here's our point. And the only role that this x plays, it's just a notational thing. It's just telling us, this x here, all it's saying is that we're going to change the x coordinate. So we get the derivative with respect to changing the x coordinate, keeping y fixed. And by contrast, we can also change the y coordinate. This is the partial derivative with respect to y. And this y here, all it's saying is that we're going to change the second coordinate, the y coordinate. But in this case, we would hold a fixed. Okay, and we're seeing how does the function change, well, as you change just one of the coordinates. Now, if you had a function of like say 1,000 variables, you would end up having 1,000 partial derivatives, one for each variable. Okay, if you have a function of 1,000 variables, you might have like the 17th partial derivative would be the one where you change the 17th coordinate, but you hold all the other coordinates fixed. And you just measure changes with respect to that one coordinate. And we'll see that, once we know about the partial derivatives, this is enough to go back to this original problem where we have sort of infinitely many directions, and we can figure out how the function changes in any one of those directions. So we would be able to, at that point, figure out how a function is changing, anywhere near the point in any direction. Okay, so here's another way to look at this geometrically. Um, we'll start with our surface. We have this function of two variables, and here's a picture of the surface. Now, if I want to calculate the partial derivative with respect to x, the first coordinate, what I want to do is hold the other coordinate fixed. And the easiest way to do that is just to intersect the whole picture by this plane. So this plane that I've drawn here, this is the plane consisting of all the points in space that have the same value, y equals b. So this plane can have any value of x, any value of z, but the y value is always b. So anywhere along this plane, if you move around this plane, the second coordinate, the y coordinate, never changes. It's always equal to b. And this is how we can measure the partial derivative with respect to x. So in other words, we're allowing x to change, but we're not allowing y to change because we're fixing everything in this plane. So if you take this plane and look at what's happening in cross section, the cross section is going to look like this. So the cross section of the plane with the surface is going to be this curve sweeping like this. Here we also have the cross section of the plane with the XY plane, and this is just the plane. Well, that cross section is this line, so anything's possible for X. Y is fixed at B, and then here we're also plotting Z vertically this way. This point here is is the point that we're interested in, A comma B. And this point here is represents the corresponding point up on the surface. And you see this curve going through this point. Well, if we want to look at the partial derivative, it's going to be given now by the slope of the tangent line in this one-dimensional situation. So what we've done in effect is taking like a two-dimensional surface, and then by intersecting it by another two-dimensional surface, this plane, we end up getting a curve, which is one-dimensional. And going back to Calc 1, the change along this curve, this slope is going to be equal to the partial derivative with respect to x at the point AB. So whatever the slope is, um, another way to look at that, and like you'll see in a second when I actually make a definition, is think about if you fix the y coordinate, then you're really looking at a map which sends x to f of xb. See, the y coordinate is never changing, so this is really just a function of one variable x, and because b never changes, and we just want to calculate the derivative then of that function. So all of this basically is like background for why we choose this as the partial derivative of f with respect to x at AB. So this is our definition. The mathematical definition just involves limits of difference quotients like what you saw in Calc 1. Okay, so in unlike Calc 1, in Calc 1 you spend a lot of time starting from difference quotients and, getting formulas for derivatives. Well, you've already done all of that. You don't need to redo that work in Calc 3. We can just use what we already know. And in a moment I'll do some examples. You'll see that calculating partial derivatives really it works the way you would think, more or less. It's not harder than just calculating ordinary derivatives. But take a moment to kind of think about this definition. What are we saying here? So again, this notation x here means that we're going to change the value of a, the x coordinate. The other coordinate remains fixed at b. So here's b, here's b. We're comparing the original value f at ab to this new value, which is close by, f of a plus h, and b. This difference represents how far did the function change between these 2 points. And then we're dividing by h. That's the distance between a plus h and a. So this term here is our delta x, and the denominator represents delta x, the numerator represents delta y, and then by taking a limit, we're getting a derivative, sort of instantaneous rate of change. Okay, so I hope that's clear. All right, something similar happens if we want to do the partial derivative with respect to y, then what we're going to do is we're going to study what happens as we change the variable y, and we're going to keep x fixed where it is and just fiddle around with y. So to keep x fixed, we're going to intersect this geometric picture with the plane x equals a. This plane cuts across our picture. Here's the point we're interested in on the surface. Here's the point downstairs in the domain. And then in cross section, we get another curve. So it's all pretty much, it's similar to what we did in the other case. Inside the plane x equals a, we have this picture. This curve represents the cross section with the surface. Here's the intersection with the xy plane. Here's the point we're interested in on both the xy plane and on the surface. And then the slope of this tangent line is our partial derivative, which is defined again by a limit of difference quotients. In this case, the partial with respect to y. For that, we're changing the y coordinate only, keeping the x coordinate fixed. So x is equal to a throughout this process. Y changes, and then here we have, this would be our delta y in this case, and this is like a delta z. Okay, are there any questions? Okay, let me come back to the slide. Um, let's just do an example so that you can see that there's really not a whole lot to this. Really, to do these calculations, it just kind of involves one idea. So here we have a function that's given explicitly in terms of x and y, and the goal is to find these two partial derivatives. So to do that, let's first compute the partial derivative function using this rule. So what is the partial derivative of f with respect to x at the point xy? Okay, when you see this, for this, we see, okay, the subscript here tells me that I'm differentiating with respect to x. And what am I differentiating this expression? I'm going to hold y constant when I compute the derivative. So when you compute the derivative of this explicit form, the only thing you have to keep in mind is that the y is just constant, and deal with y as a constant the way you would deal with it if it was something, more explicit, like if, say, y was 2, this would be the number 8, and this would also be the number 8, right? If so, for example, let's say y was equal to 5. In this case, you'd be staring at the polynomial x squared plus 125x squared plus 50, okay, in this case. And if I said, what's the derivative of that? You could say, well, that's easy. I took Calc 1. The derivative is 3x squared plus 250x and plus 0. Okay, so when you're taking a derivative here with a general y, and you're taking a partial derivative, all you have to do is just imagine that y is constant. When you differentiate, the derivative of x cubed is 3x squared. And if y is a constant here, we get the constant times the derivative of x squared. So the derivative here will be 2x times the same constant. And then here, I'm just taking a derivative of a constant. There's nothing involving x. There's no variable, so its derivative is 0. And that's basically it. So that's the partial derivative with respect to x in general. And then now we can compute the partial derivative with respect to x at a point just by substituting. This is 3 times 2 squared plus 2 times 2 times 1 cubed. This works out to, I guess, 16. Okay, similarly, if we take the partial derivative with respect to y, going back to our original function, um, when you take the partial with respect to y, at this point now you have to imagine x is the constant. So what's the derivative of x cubed? If x is constant, the derivative is 0. For the second term, we have a constant x squared times y cubed. The derivative in that case is going to be 3x squared y squared. Okay, so just remember in the second case, I'm differentiating with respect to the variable y. In the last term, the derivative with respect to y of 2y squared is minus 2y squared is minus 4y. And so to calculate that at a given point, again, we can just substitute minus 4 times 1. This works to 8. All right, so I hope all of that is clear. If you have questions, please let me know. You can send me an email if you want. You can also ask me now if you want to. Let me just say that, for the partial derivatives, you'll see there's lots of notations for it. This is not an exhaustive list, but it gives you some idea of the importance of partial derivatives because there are so many different notations available. So here's the first one I showed you was the partial derivative with respect to x. We write f with a subscript x at a generic point xy. A lot of times you'll see me just write this. Just to simplify the notation, I'll drop xy from it, except when I'm evaluating it at a specific point. This shouldn't lead to any confusion, so we think of f, and then we're differentiating that to get f sub x. Um, in many ways, this notation I like better. You'll see this a lot as well. This is like a df dx. We use a script d here to indicate, it just kind of reinforces the idea that this is a partial derivative. It's only telling you a part of the story about how the function changes. So it's the how the function changes relative to the x coordinate. Um, Here, we'll also think of d by dx as an operator, which operates on functions. So think of like this is like the idea of like we want to differentiate something with respect to x. What do we want to differentiate? It's this function. We'll sometimes write this. If z is equal to f of xy, we sometimes just write dz dx. This kind of notation is used a lot if you have functions of like, say, 1,000 variables. You're going to run out of letters long before you get run out of variables. So oftentimes something like this will be used where the one here is just simply indicating we're differentiating with respect to the first coordinate. Down here where it's f sub y, this is differentiating with respect to the second coordinate. You could have the third coordinate, the fourth coordinate, etc. Um, this notation here is, this last notation is kind of consistent with the way that you would do a partial derivative using something like Mathematica. So I'd say, take a look at these various notations. They all mean exactly the same thing. In this course, what you'll mostly see is I'll be writing either this or this most of the time. And then these are the rules to find the derivative with respect to x. Basically, just treat y as a constant. Try to imagine it's a constant, not a variable, and then just differentiate usually using the rules you learned in Calc 1. And the same rules, the rules you learned in Calc 1 apply because we're essentially starting at the same point that you started in Calc 1. There's an extra variable in all of this, but that variable doesn't actually change, so it's just you can sort of ignore it in a way. Okay. So let's look at this next example. I'll just do a few more examples. Um, Here's an example using the chain rule. F of xy equals sine of x over 1 plus y. Calculate df dx, the partial with respect to x, and df dy, the partial derivative with respect to y. So, so df dx, I'm thinking of this as an operator, d by dx applied to the function f. So that's d by dx of sine um, x over 1 plus y. Now, since I'm differentiating with respect to x, this part is just a constant. So you think about how would in Calc 1, how would you have differentiated d by dx of sine of 8x? Well, first you take the derivative of sine as cosine, and then you have to multiply this. Let's see, I kind of ran out of space there. Okay, so first you differentiate sine goes to cosine, and then after that you can bring the d by dx inside by the chain rule. D by dx of 8x, which here we get 8. So the final result being 8 cosine 8x. Over here on the other side, our constant here is this constant in the denominator. This is actually x multiplied by the reciprocal of 1 plus y. And so the derivative works the same way. Derivative of sine is cosine. So you just take cosine x over 1 plus y, and then we'll have, by the chain rule, sort of d by dx of x over 1 plus y, bringing d by dx into the inside. And now if you think about this as just a constant multiple of x, the derivative is that multiple. So we get cosine x over 1 plus y times 1 over 1 plus y. And that would be the final answer. Similarly, d by dy. So here I'm applying a sort of operator d by dy to the function f. D by dy applied to sine x over 1 plus y. And again, the first thing I can do is differentiate sine. Derivative of sine is cosine. And by the chain rule, we have d by dy of x over 1 plus y. Okay, and in this case now I'm differentiating with respect to y, so this stuff is all part of the function, but the constant in this case is x. And you can pull that constant out if you like and then differentiate the rest of it. So in any case, here you should think about how would you deal with something like this if instead of x over 1 plus y, it was like 15 over 1 plus y. So Because we're differentiating with respect to y, this is just some constant. So if you don't know what to do, maybe sort of mentally replace the x by something that looks more like a constant, like I don't know, 7 or 15, 20, whatever. And then think about how to do the derivative that way. Anyway, at the end of the day, we'll get this. Derivative d by dy of that is works out to be minus x over 1 plus y squared. Okay. Let's see. There seems to be a missing equation here. So, let me do another. That was surprising. All right. So somehow the equation in that example got let me try this again. So I'll just do another example and then I'll fix this in the notes. Um, let's see. So suppose we have something like this. We have in this case a function z which is defined implicitly. So here's a type of problem that you'll probably get on the next homework. You'll have a situation like this where we think of x and y are independent variables, and then z is implicitly defined as a function of x and y. Okay, I don't know if this is like this particular example. You could probably, with a little work, write it out explicitly. Z is an explicit function of x and y, but let's just say this is all we were given. And then the problem is to find the partial derivatives of z with respect to x and y. So what should we do? Here, the setup is this. So we have z as a variable which depends on x, z depends on y, but the variables x and y are independent from each other. So this is a kind of tree diagram which is just showing the dependence of one variable on the next. And to find the partial derivative with respect to x in this case, what we'll do is we'll take our equation like this and think about now applying the operator d by dx to both sides of this relation. Okay, and we'll just kind of formally compute. So the derivative with respect to x of x cubed, that's going to be 3x squared. The derivative of y squared x, well here y is a constant because y is independent of x. So this is just a constant, and then the derivative of x is 1. So the derivative here is y squared. For the next term, let me actually just write this out a little bit. I'm going to do this in an extra step. I'll write it as d by dx of x times z. And then here we'll have, let's do this also separately. And then on the right side, the derivative of 0 is 0. Okay, so copying the first few terms. Now let's look at this term here. We're taking a derivative with respect to x, and this is a product of two functions, both of which depend on x. So x depends on itself, and then is a function that depends on x. So we just use the product rule here. We take the derivative of the first term, 1, times the second term, plus the first term, x, times the derivative of the second term. This is dz dx. Okay, and notice that in this kind of a problem, this is the thing we're trying to solve for. So we're looking for dz dx. Let's go move to the next term. D by dx of y over z. Well, y is a constant, so I could just pull that out. And then I'm going to have d by dx of 1 over z. So let's see, pulling out the constant y. And if I differentiate 1 over z, that's minus 1 over z squared. And then by the chain rule, dz dx. Okay, and so that's probably the hardest part of this. I don't think it's that hard if you kind of think about which variables depend on which other ones. But anyway, the basic strategy is just apply d by dx to this whole equation, calculate everything out. The last part would be we want to solve for dz dx, so I want to collect together everything involving dz dx on one side. I've got x and then minus y over z squared dz dx. And then the rest of the stuff, this part doesn't depend on, doesn't have dz dx in it, so I'll move that to the other side. Get minus 3x squared minus y squared and then minus z. And so dz dx is minus 3x squared minus y squared minus z over x minus y over z. Okay, this looks complicated, but really it's not that complicated. This is the hardest part is just making sure you copy your own handwriting. You don't introduce some errors. I haven't done anything really that demanding. It's just that there's a lot of terms here. From a distance, this all looks pretty ugly. But if you do this yourself and go through these steps, you'll see that most of the time I'm just copying from one line to the next, doing some small calculations, and here a little bit of algebra at the end. Okay, maybe let's do the other case as well. So let's okay, so let's just do the other case, and now we'll look at what's the derivative with respect to y of z. I'm using this implicit definition. Well, we take d by dy, apply it to both sides, and what do we get? Well, the derivative of x cubed is 0. With respect to y, x cubed, that's just a constant. There's no y dependence anywhere. That term disappears. The second term, y squared x, its derivative is 2yx. And maybe I'll just do what I did before. Let's look at these two terms, d by dy of xz, d by dy of y over z. Okay, so d by dy of xz, well, x is a constant. Here x is a constant. I can pull that out, and I'll get plus x times dy dz. And here's the thing I'm trying, uh, let's see, whoops. Okay, that's more like it. So it's x times dz dy. For the next term, I've got some kind of a quotient rule going on, or I'll think of this as like y times z to the minus 1. So it's the derivative of the first times the second plus the first times the derivative of the second. And so we get this. This is all equal to 0. Last step, we collect everything involving dz dy. So this is going to be x minus yz to the minus 2 dz dy. Okay, so that's, here I collected this term and this term. Everything else doesn't depend on dz dy, so it goes to the other side. Get minus 2yx minus z to the minus 1. And then now we can solve for dz dy. All right. And hopefully I got to the end of that without some typo that's gonna, well, I think that's right, unless there was some other typo I missed. Hopefully that makes sense to you. Maybe I'll leave you with this. I won't do this one, but you guys can think about it. The principle is still the same. If you're talking about functions of three variables, computing a partial with respect to x means that you just think of x as the only variable and everything else is a constant. And just differentiate away. So maybe I'll do the first one for you, and you guys can think about the other two. F of x is going to kick out, we'll get a y, e to the xy, natural log z. All right, so anyway, I hope that made sense to you. If you have any questions, please feel free to send me an email. I'll try to clear it up, or I can meet with you. And see you on Friday. Hopefully, Friday. Well, okay, so we'll see how it goes. If the university open on Friday, then I guess the exam will go through, and if the university is closed, we'll figure something out. So anyway, have a good day.
I have just a really quick question about a problem on the one of the practice exams. It's just a very